Stellar temperatures and sizes. Okay, let's start with blackbody curves. Blackbody curves are basically the thermometer of astronomy. They tell us the temperature of different celestial objects. That temperature is based on a pretty simple equation that's based on the peak frequency of the object. See, on a blackbody curve, you're plotting the intensity, as you see here in the vertical axis, the intensity of different frequencies of radiation being given off by the object. And the peak frequency, the top of the hill, is what we use to actually determine the temperature. In this chapter, it'd be the surface temperature of a star. Interestingly enough, the shape of the curve is the same for all objects. You have your own blackbody curve. We could plot out the infrared that your body gives off, and you would have a curve that happens to be the same shape as the curve for, let's say, a star. Now, the star's curve is going to be much more intense and things like that, and it shifts to the left and right, but the shape of a blackbody curve always stays the same. And that peak frequency allows us to find the temperature of different objects. So let's watch a little video clip here, and I'm going to stop it at
the blackbody or Planck curve with the temperature of a heated object.
So we start out here with a blackbody curve down here that's completely in the infrared section of the spectrum. This is a rainbow right here, supposed to be representing visible light, and then you have even higher energy than visible light is ultraviolet, beyond violet. Ultraviolet, lower energy than red, infrared. So here's a blackbody curve of an object that's only giving off infrared. Maybe the hood of your car. After your car has been running and you put your hand over the hood, and you can feel the heat coming off. Your body would have an infrared curve as well, right? You're not glowing, I hope. So all of your heat that you're giving off would be in the infrared. So this is a blackbody curve of an object that is just warm but not glowing. Let's continue.
As the object heats, the shape of the curve remains the same, but the peak of the curve shifts. The visible region of the spectrum is indicated by the vertical color bar from red to blue. A temperature indicator is at the lower left. As temperature rises...
Let's stop right there. As you can see, in this case, it's still peaking in the infrared, but now some of the radiation now is being given off in visible light. That means the object has started to glow. And what color is it going to glow? It's going to be red or orange or yellow, because we are now into that side of Roy G. Biv, that side of the rainbow. You can have stars that are a very deep red. The Crimson Star is the name of a star I found before. And because they can have red with absolutely no blue or violet mixed in. That's possible. You can have red stars, orange, yellow, and so forth.
The red end of the spectrum fills up first, causing the object to glow red, then orange red, then yellowish red. It eventually becomes white hot when the entire visible portion of the spectrum fills in a roughly uniform way.
So now we have a situation where you have a good mix. Let me back it up just a bit here if I can. A good mix of all of the colors of the rainbow, which is going to be white. So you have a lot of white stars that have a good mix, and that one is peaking in the visible part of the spectrum.
At extremely high temperatures, the peak of the spectrum moves beyond the visible range toward higher frequencies, and the resulting tilt in the portion of the spectrum that remains in the visible range causes the object to appear slightly more blue than white.
So now we have a peak clearly in the ultraviolet, beyond what humans can see. Stars like the Pleiades cluster stars are so hot, some of them, that they peak in the ultraviolet. But what do we see as humans? Well, we see a mix here of all the colors, but the blue-violet side is stronger, more intense than the red side. What does that mean? Well, it means you have a very brilliant white. It's kind of like the difference between having a lamp with an incandescent bulb, and it's kind of a nice warm yellowish light, and then you go into the bathroom and you have a fluorescent light that's a much, and that's what we see with stars. So let's take a look at some colors here. Let's take a look now. Sorry about that. There we go. At the color of some stars here. Don't be confused on the sizes, okay? Some of the largest stars in the sky are actually of type M. Just pay attention to the color. You can have very reddish stars, orangish stars, yellowish stars, and then when you get to F and A type stars, those are going to be very, very white stars. The most rare type of stars are the B's and especially the O's. I mean, these are 1 in a million type stars. And again, they're not really a pure blue. We call them blue giants sometimes, but it's really more of a bluish white. Now, what about these letters? Well, these letters go back to the ladies at Harvard, the women astronomers at Harvard, led by Annie Jump Cannon. They analyzed hundreds of thousands of stellar spectra, and they came up with letters. And then what happened was later they realized, after doing a lot of these spectra, that the letters, the spectra they were seeing, were actually based on temperature. They didn't understand that at first, and so the letters got rearranged over time to kind of this odd lettering here, O, B, A, F, G, K, M. That's going from hot to cool, O stars being the hottest and by far the most rare type of star, down to the M types, which are the coolest and by far the most common type of star. And even starting in the 1800s, you started having mnemonics to help people remember. So for example, the original one, O, be a fine girl, kiss me, to help remember the 7. Oh, be a fine girl, kiss me. Kind of a funny one from the 1960s. I guess the women thought that original one was a little sexist, so they came up with this one. How about this one? Only boys accepting feminism get kissed meaningfully. And of course, my own students have taken a shot at this over the years. Old bananas, anger, furry giant killer monkeys. That's one I remember from years ago. Now, Annie Jump Cannon and the group of astronomers at Harvard decided to take the 7 letters and give each of them 10 numerical subdivisions from 0 to 9. So the hottest B stars, for example, are B0s, then B1, then B2, down to B9 would be the coolest of the B stars, and then you would get to an A0, a little cooler than that, and it goes from A0 to A9 and so forth. Some well-known stars, our sun is type G, and specifically a G2. Stars like Vega and I believe Sirius are type A's, and famous Betelgeuse is a type M. Speaking of Betelgeuse, let's talk about the size of stars. The largest stars are called giants. A couple examples there. Arcturus, 23 times the diameter of the sun. And Aldebaran, the Eye of the Bull, is another giant star. But there are bigger stars, supergiants, more than 100 times the diameter of our sun. They are to our sun what our sun is to the earth. And the most famous example I already mentioned is Betelgeuse. There's also Antares is a good one as well. At the other end of the scale, small stars are called dwarf stars. You notice it says less than or equal to the diameter of the sun. Interesting, right? The sun is actually sometimes called a yellow dwarf star. But there are white dwarfs and red dwarfs. White dwarf, Sirius B is the one that I would want you to know. Obviously that orbits with Sirius, the brightest star in the sky. It has this white dwarf companion. Procyon does as well, has a white dwarf with it. And then red dwarfs are so plentiful. Proxima Centauri orbits in the same system as Alpha Centauri, but Proxima is actually slightly closer. So if you're ever on Jeopardy and Alex Trebek asks you the closest star other than our sun, it's actually Proxima Centauri, which is a red dwarf. We mentioned Barnard's star in the notes a couple days ago. That's another red dwarf. So these white dwarfs are incredibly small, only the size of the Earth, as you can see, and you see how they compare, let's say, to our sun. I don't really consider those to be stars anymore. They're really the burned out core of a star at that point. No more fusion left. We'll get to that later. But let's talk about the fun ones here, the big stars, the giant stars. So let's see how our sun does stacked up compared to some other stars. Our sun was the king here for a while. No more. Our mighty sun now just a little marble at the bottom of the screen. Jupiter, which was the king of first semester, now Jupiter just 1 pixel on the screen. Unbelievable. Our Earth is invisible at this scale. We don't even merit an entire pixel there. What's the hottest star on the screen? Well, that would be Sirius. As you can see, it's white hot. Pollux is a star in Gemini. It's one of the heads of the twins. And Arcturus, an orangish colored star. It's one of the brightest stars in the sky. And it's in the springtime. Beautiful, beautiful star. And so it's our new king. Oh, but wait. Arcturus is just a giant star. So take a close look at Arcturus. We'll see how it stacks up compared to some super giant stars. Oh boy. So now Arcturus, there it is. It's just a marble at the bottom of the screen now. Our mighty sun, which can hold over 1 million Earths inside of it, is now 1 pixel in size. Jupiter's invisible. It's insane. The hottest star on this screen is Rigel. That's in Orion. And I believe it's maybe a type B. It's very brilliant white in the sky. Aldebaran is another giant star like Arcturus, but then we get to the real big boys here, the supergiants. We have Betelgeuse, I already mentioned, and Antares. Antares is in Scorpius. It's kind of the heart of the Scorpion in the summer sky. Look south and you'll see it on the southern horizon. It's really, really gorgeous, right in the body of the Scorpion. So as you can see, and Antares is not the largest star that we know of. Stars like VY Canis Majoris are even larger than it. So it's pretty amazing how large these stars are in space. Thanks for listening.